Welcome back to the Mountain Morning Show. All right, this is going to be really cool. I'm excited. I'm sitting next to Steve Wasserbaech, who is the professor of physics, right? Physics at Utah Valley University.
Correct.
So yeah, I'm so excited. I'm blundering here a little bit, but so we're going to be talking about CERN and the Higgs boson, and you've been involved in all of this study, and they've actually discovered the Higgs boson. They think, is that right?
That's correct.
So tell me all about this. I'm totally stoked.
All right. So about 2 weeks ago, 2 experiments at CERN announced the discovery of the Higgs particle, or the Higgs boson. The experiments are called CMS and ATLAS, and they've been under preparation for many years. They started collecting data in 2010, and I joined the CMS experiment in 2009. The Higgs particle was proposed a long time ago. In the 1960s, Peter Higgs and others were trying to understand what is the origin of mass. The particles in the universe have mass,
Right.
which is related to inertia. Mass tells you how hard it is to get something moving or to slow it down again. And they wanted to understand where that comes from. Why do particles have mass? And one idea that was proposed is that the whole universe is filled with a kind of a field, which is now called the Higgs field.
Okay.
And the idea is that when particles interact with this Higgs field that's everywhere, it gives them the property that we recognize as mass. Some particles are heavier, have more mass, and that just means they interact more strongly with the Higgs field.
Okay. And the way that, because you can't just see this stuff, the only way to find it was to build a giant super collider, right?
Correct.
So let's talk about the giant super collider
Well,
first.
the Higgs field is certainly not observable, but the idea was that we might be able to observe Higgs particles, which are little clumps of Higgs field energy. So that's what was discovered. And in order to make the Higgs particles, we needed to be able to bring a lot of energy together. Well, a lot is a kind of relative term. The collision energy of the protons in the Large Hadron Collider for this discovery was equivalent to about 8 mosquitoes worth of flight motion energy.
Wow, so not a tremendous amount of energy.
No, for a human scale, the 2 protons colliding have microscopic amount of energy, but for 2 protons, that's really an incredible amount of energy. And it needed to be large because the Higgs particle itself has a lot of mass, and conversion of energy into mass is the key to these collision experiments, and so a high energy collider was needed. The Large Hadron Collider is the highest energy and largest particle accelerator in the world.
This thing is a 17-mile circle, right?
Correct.
It's buried, as I understand, 100 meters under the ground in between Switzerland and France.
It crosses the border several times.
Wow. And you send these particles around this 17 miles many, many times.
Right. There are bunches of protons traveling in opposite directions.
Okay.
And they're going virtually the speed of light. They are able to go around the 17
And here's a picture of the collider here.
Right there you see inside the tunnel, which is 100 meters under the ground. Those big blue things are magnets whose job it is to bend the protons to follow the curve of the tunnel. Protons want to go straight. And the magnetic field causes them to bend.
Okay.
The protons travel around those 17 miles 11,000 times a second.
Wow.
And they're brought into focus and into collision at certain places.
And this focus is very, very small. We're talking the size of a human, diameter of a human hair.
Smaller than that. The bunches are sort of long, but in cross-section they are smaller than the diameter of the human hair, and those bunches pass through each other, and 100 billion protons in each bunch, and most of them miss. And maybe 10 or 20 in each bunch crossing will give some kind of collision, and once in a while there will be something really interesting happening.
And when that happens, it has a very, very short lifespan, right? I forget what you guys call it.
Most of the particles that are created are unstable.
Right.
The Higgs included. The Higgs particle virtually decays instantly. It doesn't even reach the walls of the pipe in which the collisions occur not even close. And
Wow.
so the Higgs particle decays into various combinations of other particles which are more stable and which can enter the detectors which are surrounding the collision points.
And so there were a lot of people who were really scared about this at first. When we first started talking about this thing, there were people saying, "Oh, please don't turn it on. What happens if we create a tiny black hole?" And there probably wasn't a lot of reason for this fear, but talk about that for a minute, because I know people were a little scared about it.
So first of all, the quick analysis is this. You're going to have 8 mosquitoes worth of energy unleashed on the universe, and it's not likely to produce a tear in the space-time continuum. Number 2, it is actually a serious possibility that black holes could be produced. 8 mosquitoes worth of energy, black holes, and those are understood to evaporate instantly. They would not suck up the whole Earth, they would evaporate.
Right. But people did think that I know there was a lot of news about the idea that in a matter of a microsecond we could all be dead.
It's a fair question to ask before we turn it on.
Right.
But another point is that collisions much more violent than these have been going on for eons because there are much more energetic particles coming from space colliding with the Earth's atmosphere all the time. So there have been thousands of Large Hadron Colliders worth of experiments done in the atmosphere, and the Earth has survived.
Kind of what happens with the light coming from our sun, isn't that sort of an idea of that?
But the particles coming from the sun are much lower energy than what's needed to really compare with our LHC collisions.
Really?
But the cosmic ray particles, which come from farther away in the galaxies, are a fair comparison. And so a careful analysis was done before the thing was turned on. And it confirmed, even under the most unlikely physics scenarios, that the Earth could not be swallowed up, and obviously it wasn't.